All right, so let's look at what Newton's calculus looks like. And his method is called the method of fluxions. That word flux sounds like change. When something is in flux, it is changing. So this is all about change. Fluxional calculus is another phrase that is used to describe Newton's particular brand or his particular take on calculus. So let's go over to the document camera and take some notes and look at a couple of problems that he would have solved and use his methods to solve those problems, and then compare them really quickly to the way we would do it. Okay, so two problems were central to his ideas, and these are going to sound familiar, I think. First of all, find the length of the space at any time. Find the length of the space at any time. I'm sorry, not find the length of the space, given the length of the space. Given the length of the space at any time, find the speed of the motion at the time proposed. So you are given a function that represents the length of the space at any time. And we might say that's the distance traveled. That's the position on the coordinate system. But we would say today and represent it today as given f of t, find the speed of the motion, how fast is it going? Well, we know what that is. That's the derivative. Find f prime of t. And by the way, it's interesting, we're talking about Newton's method of calculus, but this functional notation is pure Leibniz. This is Leibniz notation for representing functions. All right, that's the first problem. Sound like calculus 1? You're given a function, you're looking for the derivative. In calculus 1, 1241, you spend a lot of time using different rules to find derivatives of just all kinds of functions. Okay, the second problem type, you're given the speed of the motion at any time. Find the length of the space. Described at any time proposed. Well, doesn't that sound like just the opposite of what we did here? Given the length of the space, find the speed. Here, given the speed, find the length of the space. So this one, we're going to represent given f prime of t, find f of t. You're given the antiderivative, and you're asked to find the original function. Okay, before we look at how he did these, let's look at a couple of, let's look at some vocabulary. A fluent was a quantity that is changing over time. We would represent that with an X or a Y, typically. Not always, but typically X or a Y. The fluxion is the speed at which this quantity changes. And Newton represented that as X with a dot over it or Y with a dot over it, whichever quantity is changing. He would put a dot over it to show you. Now I'm talking about how fast it's changing, talking about the speed. Okay, a moment is the amount by which the fluid changes. In an infinitely small period of time. And he said, let little sigma, the little Greek letter sigma, represent that infinitely small period of time. Okay, so think about it for a second. The amount by which the fluid changes, that's a distance. It's moving from here to there, and from here to there is the amount that is changing. That distance that it's changing, we know can be represented by the rate times the time. Distance equals rate times time. So the distance, which is the moment, is equal to the rate, which I'm going to represent with x dot. That's how fast it's changing, times the length of time we're talking about, and that's sigma. So the moment, that amount by which it changes in that infinitely small period of time, is x dot times sigma. So if we're talking about the quantity x in a very small period of time, sigma is the length of time. It moves from x to x plus x dot sigma. Okay, well, there's our vocabulary and some of the symbols that we're going to use. And so here is problem type number 1. We've got y equals x squared plus 3x plus 6. And the question is, find the speed at which y is changing compared to x. And that will be represented with y dot over x dot. The change in y compared to the change in x. And we're just going to follow through the steps that Newton did. All right, first thing to do is replace y with y plus y dot sigma and x with x plus x dot sigma. In that tiny period of time, sigma, y is going to move this amount, y dot sigma. So it will move from y to y plus y dot sigma, and x will move from x to x plus x dot sigma. Okay, so we're going to make this substitution back in our original equation, and we get y plus y dot sigma equals x plus x dot sigma squared plus 3 times x plus x dot sigma plus 6. And let's do the math and simplify. Y plus y dot sigma equals x squared plus 2x x dot sigma plus x dot squared sigma squared plus 3x plus 3x dot sigma plus 6. Okay, second step, subtract equal amounts from both sides. You might look at that and say, well, wait a minute, I don't have the same thing on both sides. Everything looks different. But don't forget, we started off with this is what y is equal to. Y is equal to x squared plus 3x plus 6. And I've got y on the left-hand side, and I've got x squared plus 3x plus 6 on the right-hand side. So I'm going to subtract those equal amounts from the left side and the right side, and that will leave me with y dot sigma equals 2x x dot sigma plus x dot squared sigma squared plus 3x dot sigma. Every single term has a common factor. So I can simplify this. And in fact, he said that's the next step. Divide each term by sigma. And I'll get y dot equals 2x x dot plus x dot squared sigma plus 3x dot. All right. And then Newton said, drop any terms left with sigma as a factor because they are, and this is a quote, because they are nothing compared to the others. All right, well, the only term that has sigma still in it is that middle term right there on the right-hand side. So once it's gone, I'm left with y dot equals 2x x dot plus 3x dot. And on the right-hand side, I can factor out x dot, and I'll have x dot times 2x plus 3, and then divide both sides by x dot. Y dot over x dot equals 2x plus 3. Okay. Now this might actually remind you a little bit of Fermat's pseudo equality method, and it should. Newton's got some more theory involved. He's got a more of a physics kind of background and is relating this more to motion and movement and velocity than Fermat was doing. He's got a little bit more justification for some of these steps, but still he's got the very same issue where right here he's dividing each term by sigma, and then he says sigma is equal to 0. Well, if sigma is equal to 0, then you can't divide everything by sigma, but he does. And I'll be darned if it doesn't work, because we know that the derivative of this function y prime would be 2x plus 3. All right, now let's get that derivative though, using the definition of a derivative. All right, just humor me here for a second. Here's our function. Here's the definition of f prime of x. It's equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And so that's the limit as h approaches 0. F of x plus h is going to be x plus h squared plus 3 times x plus h plus 6 minus f of x, x squared plus 3x plus 6. And all of that divided by 6. Well, remember a little while ago when we substituted x plus x dot sigma? We're doing the same thing here, except it's an h instead of an x dot sigma, because I get the same expansion x squared plus 2xh plus h squared plus 3x plus 3h plus 6 minus x squared minus 3x minus 6 all over 6. And remember over there where I subtracted quantities, same quantities from both sides? Well, right here, when I do this subtraction and simplification, I get the very same result. Equals the limit as h approaches 0. 2xh plus h squared plus 3h plus 6. Oh, the 6 is gone. I thought something didn't look right there. Okay, 6 is gone over h, not 6. And now divide by h, just like I divided by sigma a little while ago. Now, the reason I can do that here is because I'm talking about a limit. I'm not really talking about h is equal to 0. H is getting close to 0, but it's not exactly 0. So 2x plus h plus 3 is what I get. And then when I evaluate this limit at 0, sure enough, I get 2x plus 3 for f prime of x. Same thing. I mean, a very similar process, but mathematicians in the 1800s came along and they arithmetized the analysis of this calculus. They rigorized it. They they did away with all the little kind of hand waving where, oh, okay, well, now it's 0, now it's not. Well, it's close to 0, so we can ignore it. No, they said there's a theory behind it. And the theory has to do with limits. Okay. All right, well, let's look at that second problem type. And by the way, we're doing just very straightforward problems here using polynomial functions as our examples. You can get more complicated with this and use some functions where you would have to do some implicit differentiation and some fairly sophisticated anti-differentiation methods, and this will all still work. All right, but the second problem was one where you're given f prime of t and you're asked to find f of t. So in this case, our example is y dot over x dot equals 2x squared minus 5x plus 6. And you might just stop right here and think about for a second, well, what's this going to equal? What should we end up with? We should end up with y equals 2x to the third over 3 minus 5x squared over 2 plus 6x plus a constant, which would be determined by the context. Okay, so Newton said, well, first of all, multiply both sides by x dot. Okay, so when I do that on the left-hand side, I'll get y dot equals, and now x dot over here is a factor of each term, 2x squared x dot minus 5x x dot plus 6x dot. And then he said for each term with x dot, multiply by x over x dot. Okay, well, that term doesn't have an x dot in it, so ignore it. I've got y dot equals 2x squared x dot times x over x dot minus 5x x dot times x over x dot plus 6x dot times x over x dot. And when I simplify everything, I'll get y dot equals 2x to the third. X dot over x dot is 1, so 2x to the third minus x dot over x dot is 1, so 5x squared. X dot over x dot is 1, so 6x. Okay, I'm getting there. So the next step is for each term, and I could have done 2 and 3 at the same time, but for each term with y dot multiply by y over y dot. So that means on the left-hand side, I'll have y dot times y over y dot equals 2x cubed minus 5x squared plus 6. And I get y equals 2x to the third minus 5x squared plus 6. Now, this is where I think Newton must have known what he's shooting for. He knows what the answer is. And he must look at that. I mean, I don't know for sure, but he's got to stop and think right now, well, how do I get from here to the function that I want? So my last rule is divide each term by the power of the fluent. So that's going to be y, that's y to the first power, so y over 1 equals 2x to the third. X is the fluent, so x to the third over 3. X is a fluent, so 5x squared over 2 plus 6x, I left off the x here, plus 6x to the first power divided by 1. And sure enough, I get y equals 2/3 x to the third minus 5/2 x squared plus 6x plus or minus a constant. There you go. That's what I expected to get. That's pretty nifty. Pretty amazing. And like I said, this works even on more complicated functions, but we don't need to get real complicated here, just showing you the idea. And again, just going through when Newton did write about his method of fluxions and he talked about this method, he was, laying out that procedure. This is what you do and how you do it to make it work and get what we wanted. When he used his method of fluxions in his book, The Principia, that was not a calculus book. That was his masterpiece of physics. He used this to get the results that helped him derive his laws of gravitation. Okay. All right. One more in calculus and we're done.